Ignite a block of TNT, and you get a violent, chaotic fireball. The energy blasts outward in every direction, following the path of least resistance. For centuries, this unrefined brute force was exactly what humans wanted out of an explosive. But by the spring of 1944, scientists at the Los Alamos laboratory realized that brute force was not going to be enough. They were trying to build the first atomic bomb, and they had just hit a wall. The initial plan was simple: use an explosive to fire one piece of nuclear material into another inside a gun barrel. But the plutonium arriving from the reactors at Hanford had an incredibly high spontaneous fission rate. If they tried firing it down a gun barrel, the plutonium would react too early and pre-detonate, resulting in a failed fizzle. An outward expanding blast was useless for this material. Detonating a plutonium core would require a level of absolute explosive control that simply did not exist in the field of physics. Physicist Seth Nettermeyer proposed an alternative idea called implosion. This animation shows how his theory was supposed to work. You take a subcritical sphere of plutonium, surround it with explosives, and direct the entire force of the blast inward. The pressure would uniformly crush the metal core into a hyperdense critical mass. But doing this in the real world is incredibly difficult. The compression takes about a microsecond. If the inward shockwave is uneven by even a fraction of a millimeter, the extreme pressure will cause the plutonium to squirt out the sides, like toothpaste from a squeezed tube. They were asking a naturally divergent, chaotic force to form a perfectly uniform, converging sphere. They had to force physics to go in reverse. This photograph captures Francis Dunn, one of the technicians on the project, setting up an explosive point in the desert. Solving this problem required a massive, multidisciplinary effort that went beyond theoretical physicists, bringing in mathematicians like John von Neumann and chemists who were working with the raw materials in the field. It was a chemist, George Kistiakowsky, who finally delivered the conceptual breakthrough. He hypothesized that an explosive shockwave didn't have to be a chaotic wall of fire. It could be shaped and focused using the exact same geometric principles you would use to bend light. This split screen illustrates his concept. Just as a piece of curved glass can force divergent light rays to converge onto a single point, a mathematically shaped block of explosive could force a divergent blast wave to flatten out into a uniform front. By treating detonation as a manipulable wave rather than an act of pure destruction, the team found a way to bridge complex abstract mathematics with physical chemistry. Actually building an explosive lens required casting two entirely different chemical compounds, each with a completely different detonation velocity, into a single interlocking shape. For the exterior, they selected Composition B, a highly energetic mix of RDX and TNT that burns incredibly fast. For the interior, they instead used Baratol, a tunable explosive mixed with barium nitrate that burns much slower. This technical diagram shows the specific blueprint they arrived at. The fast-burning Composition B is cast on the outside, acting as the high-velocity layer. The slower Baratol is seated underneath it, shaped as an inner core. Looking at the yellow travel paths in this graphic, you can see the microsecond timing in action. When the detonator fires, the fast wave races down the outer edge. Meanwhile, the slower core delays the blast traveling straight down the center. Because the center is held back, the outer edges have exactly enough time to catch up, allowing the entire wave to exit the lens at the exact same moment. This precise geometric marriage of a fast chemical and a slow chemical successfully tamed the detonation into a perfectly flat, uniform wall of pressure. Executing this in reality left zero margin for error. If there was even a microscopic air pocket trapped inside the cast Baratol, the shockwave timing would stagger, and the entire weapon would violently fail. To make matters harder, 32 of these lenses were packed in a sphere around the plutonium. They had to be triggered simultaneously. Physicist Luis Alvarez solved this by inventing an electronic bridge wire detonator, ensuring every single lens fired in the exact same microsecond. This photograph shows the result of that effort. On July 16, 1945, at the Trinity test, the lenses fired. The perfectly symmetrical expansion of the fireball clearly proved that the implosion mechanism successfully compressed the plutonium core. Overcoming the spontaneous fission rate of plutonium proved that human engineering could deliberately override the chaotic, natural forces of chemical detonation. The research at Los Alamos changed how engineers approach explosives, moving from crude demolition to high-precision engineering. This patent drawing illustrates a parallel application. Physicist James Tuck worked with shaped charges, relying on the Monroe effect. In Figure 2, removing a concave section of material forces the blast to fold inward, concentrating the energy into a penetrative jet. The exact geometric logic required to crush a plutonium core was now being used to turn raw explosive power into an engineered scalpel. This historical photograph of an oil derrick represents how that scalpel is applied terrestrially. Today, heavily engineered shaped charges are used to safely execute controlled building demolitions, and they are sent deep underground to radially perforate subterranean bedrock to tap complex oil and gas wells. This image of a space shuttle launch shows another critical modern application. To safely detach the solid rocket boosters during flight, aerospace engineers rely on explosive bolts and separation mechanisms that must fire with absolute microsecond reliability. Modern physics research still relies on these principles. Using additive manufacturing and 3D printing, laboratories produce complex plane-wave explosive lenses to create uniform shock loading for high-pressure testing. A project focused on a single wartime weapon ended up developing a byproduct that redefined explosive science: absolute physical precision. By treating the release of chemical energy as a wave that can be mathematically steered, the explosive lens provided the technical blueprints for modern precision demolition, deep earth oil recovery, and orbital separation systems.